Okay, so before we get started, just a couple of quick announcements. Homework 4 is due Sunday, okay? How many of you guys have started homework 4? Almost everybody, okay, that's good. Homework party, if you guys are stuck on the homework, if you're struggling with anything, homework party is great. Please go to homework party. It's actually sort of fun in a way. 2 to 5 p.m. tomorrow, somewhere in Corey. It's on the 5th floor of Corey. I don't remember the exact room. I want to say 521, but that's probably wrong. It is 521. 31. Thanks. Okay. So last time we covered this concept called superposition. That was basically how we analyze circuits with multiple sources. What we did was we shorted out voltage sources, opened up current sources, and did the analysis multiple times. And so we could analyze a number of different simpler circuits. The other thing that we talked about was Thevenin equivalence. So we can take any linear circuit and turn it into a voltage source and a resistor. Okay? And as far as the terminals across which we generate this Thevenin equivalent circuit are concerned, it's the same. So today we're going to talk more about this, more Thevenin equivalence. Before I get into that, I want to redo the example at the end of last lecture because I think I wrote something that might have been a little bit misleading in that it was wrong. So here's the bridge circuit. We've analyzed this a handful of times now. What I want to do with this bridge circuit is I want to find the Thevenin equivalent circuit as seen by these two terminals right here. So here's my voltage V out. I've got my V source. I have R1, R2, R3, and R4. Okay, and if you remember from last time, we determined that the output voltage, which in this case, if I leave this as an open circuit, is equal to the source voltage times R2 over R1 plus R2 minus R4 over R3 plus R4. Right? And we've done that analysis a handful of times now in lecture. It's basically just two voltage dividers, right? And I want the voltage difference across those two. Okay, everybody clear on that? Good. Now what I want to do is find the output resistance, R out, or equivalently, the Thevenin resistance. Now how would I normally do that? Well, okay, I have to short out all the voltage sources, open up all the current sources, and then find the equivalent resistance across these two terminals. Okay? So let's do that real quick. So now I short out where my voltage source used to be. Draw my circuit again. Here's R1, R2, R3, and R4. And I want to find the resistance across these two terminals. Okay? So normally the procedure for doing this is, what I would have to do here is attach a little voltage source, just like that, and measure the amount of current. Let's call this I test and V test. So this is actually imaginary, right? I'm doing this purely for the sake of analysis. If I went to the lab and I took an ohm meter, I wanted to measure the resistance across two terminals, this is actually what that device would do. It would apply a voltage and measure how much current it needs to provide, okay? And then back out the resistance from Ohm's law. But in this case, it turns out that this resistor configuration is actually something that I've seen before. Right, so let me redraw the circuit the following way. I want to find the resistance across these two terminals, and that short circuit, I'm going to draw down the middle, okay? that clear what I did? All I did was I took this short circuit where the voltage source used to be, and I drew it down the middle. Now it's a little bit easier to see what's going on here, right? Do you guys recognize this circuit yet? They're in parallel, right? So things start to fall into this parallel configuration that we're so used to. And if I just make it very explicit, we've got one terminal here. The other terminal over here. Here's R1, R2, R3, and R4, where I want to measure the equivalent resistance, REQ, across these two terminals. Now, is that clear to everybody? All that I'm doing is changing the topology, right? I'm moving things around to make it look like something that I've seen before. There's nothing stopping me from doing that, right? And so now I can actually calculate the equivalent resistance is R1 in parallel with R2 plus R3 in parallel with R4. Does everybody see that? Okay, so then I'm done, right? I've found my Thevenin voltage source, got that over there, my open circuit voltage, and I have my equivalent resistance. So this circuit if this is V out, this is R1, R2, same circuit, R3, R4, can be rewritten, at least from the perspective of these two terminals, as the following. Here's my V out. This Thevenin voltage source is that voltage over there. So that's Vs times those two R2, R1 plus R2 minus R4 over R3 plus R4. Right? That's the value of my voltage source. And my resistance is R1 parallel R2 plus R3 parallel R4. Okay, so I found the Thevenin equivalent of my original circuit. Okay. Now, why would I want to do this? How does this help me? Someone hands you this circuit, and they tell you, I have the circuit for you. I want you to attach some load to it. How would you analyze very quickly, regardless of what your load is, what the resulting voltage will be across those two terminals? Previously, we would have to go in, okay, let's say my load is a resistor, and I'd have to put this resistor here, and I'd have to do nodal analysis, right? And that tends to be somewhat time-consuming and difficult at times. Now what I can do instead is look at my Thevenin equivalent circuit and put that same load here. And here the analysis is much easier, right? What kind of circuit is this? They're in series, so the voltage will be, it's a voltage divider, right? There's some voltage division between my Thevenin equivalent resistance and my load resistance. Okay? Now you can imagine this circuit is a relatively simple network, you'll find. It's just a bunch of resistors, right? But imagine I give you something more complicated, like an amplifier. Like I tell you, I've got this sweet audio amplifier, okay? And it's got some gain and some output resistance. You can very easily tell, if you attach your speakers to it, how your speakers are going to perform. You don't need to know anything that's going on inside the amplifier at all. It doesn't matter. Okay? But what information do you lose when you make a Thevenin equivalent circuit? If I just give you that equivalent circuit, and I don't tell you anything about what's inside, pretend you never saw this. Do I know anything about what's going on inside the circuit?
We do not know like all the other currents. We just know the current for total.
Yeah, so the answer is I don't know anything about the currents that are inside the circuit. If I just give you the Thevenin equivalent, do I know what this current is going through this resistor? No. Do I know this voltage across this resistor? Necessarily? I guess in this case I would. That's a bad example. Do I know any of the currents or any of the voltages? Yeah.
I have a question. It's like, let's say in the original circuit, you add a resistor to it, but does the location, like the position where you add the resistor in the original circuit matter? Because like when you translate this into the equivalent circuit, you always put the resistor you just add into series, right?
Yes.
But in the original circuit, you can add it in multiple different positions, so do that matter?
Yeah, okay, so the question is, if I add a resistor in an arbitrary place to my original circuit, does that change the equivalent circuit? The answer is yes, right? So if I just take a resistance and add it here, some fifth resistor, that's not across the terminals that I determined the Thevenin equivalent circuit. This will change the equivalent circuit, right? And you can see that very clearly, right? Instead of R3 parallel R4, I'll have R3 parallel R4 parallel R5, right? This equivalent resistance has changed, okay? And same thing will happen, my voltage will change, right? Good question, yeah. So you could do that. I could figure out the equivalent circuit across these terminals instead of these and redo the analysis and determine how R5 changes things. But usually what will happen is you're given just this circuit and you're asked to say, okay, what's the Thevenin equivalent across these two terminals? And you assume that the circuit itself does not change. All you do is load the circuit at these two terminals, okay? All right, so one last thing about this. There is an alternate way of finding the equivalent resistance, and that's by first finding the open circuit voltage and then finding the short circuit current. So I want to do that because I think I wrote something on the board. It may have been very confusing. I just want to redo that. Again, my same circuit. Same as before. R1, R3, and R4. V source. To find the short circuit current, I short out my two terminals, draw a perfect wire between them. What I want to do now is find this current I short circuit. Do you guys remember why it's in this direction and not the other direction? Yes, so the answer is because when we did the Thevenin equivalent circuit, when we had the open circuit voltage, the plus side was here and the minus side was here. So by passive sign convention, the short circuit current should be from plus to minus. Okay? Now, what I can do is write the nodal equation for this node right here. Right? I have some current through R1, some current through R2, and some short circuit current that I'm trying to calculate, right? So in this case, if I sum the currents at that node, I'm going to call this node, this node, call it node, that's going to be 0 if I write it this way, minus IR1 plus IR2 plus I short circuit. Okay? Just summing the currents into that node. Right? Cool. So then I short circuit is equal to IR1 minus IR2. Now what about over here? This is the same one, right? It's the same node. So I'm treating them as different nodes, but in reality they're the same. Nothing's stopping me from doing this necessarily. What I've done is I'm going to write two different KCL equations and set them equal to each other. So over here I have some IR3, some IR4, and again, some of the currents, 0. In this case, we have minus I short circuit, minus IR3, plus IR4. And I can use this system of equations in addition to Ohm's law to solve this. I don't have to, because I already have the Thevenin equivalent resistance and Thevenin equivalent open circuit voltage. So I already have the equivalent circuit. This is just how you would this is how you would solve for the short circuit current. Okay. Right. Now, just as a reminder, I want to go through this again, this sort of proof of why Thevenin equivalence works. I tell you I have some circuit, some linear circuit. It's got voltage sources in it, current sources, resistors, maybe some dependent sources, style points. And I've got two terminals here, some voltage across them. We know from superposition that this voltage is equal to some sum of alphas, alpha m, times all the voltage sources in my circuit. This is the sum over all the voltage sources in my circuit, plus some sum n of all my current sources. So some value beta times all the current sources in my circuit. Right? So this is what I call the open circuit voltage at these two terminals. Okay? That's just from superposition, right? I've already demonstrated that that's true. So now what I'm going to do is I'm going to load the circuit with a current source. Call that lowercase il. And again, from superposition, I know that the open circuit voltage, when this current is equal to 0, is just that. It's not going to be changed, right? Because when I apply superposition and I apply that to this current source is an open circuit, no voltage, or no current, excuse me. How now does this current loading affect the circuit? All it's going to do is the voltage will change by some negative IL times a factor R. Okay? So if I plot this circuit's so-called IV characteristic, on the y-axis I have the voltage, on the x-axis I have the current that I load the circuit with. What's this point going to be? What's the y-intercept here? What's my voltage when the current is 0? Doesn't exist? No, it does exist. What would the voltage be when my current is 0? So first of all, what do I do with this current source when the current is 0? Open circuit, right? Open circuit means no current. Okay? So what will the voltage be? It'll be the equivalent voltage, right? It'll be the open circuit voltage, which I know is equal to this expression right here. And I'm going to call this VOC. That's right there. And I know that the response of my circuit to a current has to be linear, right? And it turns out that the slope of this line is R. Okay, is that clear to everybody? Now let's do that same analysis for a very simple circuit. Specifically, this one. I've got some V, source, some resistance R, and over here I'm going to do the same thing. Patch a current source, IL, I load. Yeah.
I think the slope there should be negative R.
Yeah. Thanks. The absolute value of the slope is R. Cool. Yeah. You have another question? No. Okay. So let's draw the same IV characteristic. So here's I, load. Here's the voltage between the two terminals here. What is the voltage when the current is 0? Current is 0, so this is an open circuit. What's the voltage here? Anybody know? Nobody knows? Or are you guys just really quiet? V Thevenin or V source? Because I wrote it as Vs over here. Just Vs. Okay? Is this clear to everybody? Yeah.
Wait, the resistor on the top is the REQ.
That is the REQ. That's the Thevenin resistance.
That's additional R.
It's not an additional R, no. And again, linear with slope minus R. So this is why equivalence works. That box of circuits that I analyzed over there is the same as this one from the perspective of these two terminals. Okay? Yes?
I guess I was confused because I imagined VS going and like being divided over the first resistor. So when it reaches the terminal, I have it lower, but VS actually represents voltage at the terminal, right?
Okay, so yes, Vs represents the voltage at the terminal when there's no current in the circuit. So let's very explicitly write out Kirchhoff's voltage law around this loop so I can show you why this IV characteristic is true. So I've got my voltage source, I have my resistor, and I have current source. Let me just make sure I get the direction right. With current IL. And here's my voltage that I'm trying to measure, V. If I draw the plus and minus terminals of my resistor like this, I call this VR. What will the voltage V be in terms of my source voltage and the voltage across the resistor? Someone want to help me out? Vs minus Vr. Good. Is this clear to everybody? We've just gone around the loop and calculated all three of the voltages in the loop. So this is Kirchhoff's voltage law. Okay? Now what is VR in terms of IS? First of all, what's the current through this resistor? IL. Did I get the direction right? Yes. IL is going into this node and out through the current source. Okay? So now I can rewrite my expression. V is Vs minus IL times R. If IL is 0, what's the voltage V? It's just Vs. It's the source voltage. Okay? That's how I can get that expression. That's how I can make that plot, and that's why these two circuits, this circuit and whatever linear circuit I have, are equivalent. Okay? This is more clear on Thevenin and Norton? Or in a second I'll talk about Norton. Haven't talked about it yet. So it turns out that there's another kind of equivalent circuit, which is exactly the same as the Thevenin equivalent circuit, called a Norton equivalent circuit. So here we've got our Thevenin equivalent. VTH, I'm going to change the names up a little bit. VTH and RTH. I can rewrite this as some current source with a parallel resistor. So here are my two terminals, and here are the circuits in their boxes that I'm trying to draw. Okay? Here we have I Norton and R Norton. Okay? So now let's see how we can make these two circuits equivalent. Remembering again that we're trying to make some circuit that has that downward sloping IV characteristic, like that one. So let's analyze it with that same current source. So here we have I Norton, my resistance R Norton, my two terminals, and I'm going to attach a current I load here. Okay? So in this case, what is the voltage across these two terminals? Yes?
What did you do from that?
That circuit is the same as this circuit. I just redrew it. We'll see that these two are actually identical, right? If we pick the correct value of I Norton and R Norton. Okay, so let's analyze it. Here's my output voltage V, and I want to find voltage as a function of the load current. So what's this voltage V? It's the same as the voltage VRN, the voltage across my Norton resistance. And what is that voltage? That's the resistance, Rn, times the current through it. We know that from Ohm's law. Now, what is that current? What is the total current going through this resistance, IRN? IN minus IL. Okay? I'm going to draw it out. I'm going to write it Rn times IN minus Rn times I L. Okay? So what is, if I draw this plot? Again, here's my load current, output voltage. What is my open circuit voltage? From this expression. What's my IL? 0. No current, no load. So the expression ends up being Rn times In. So my open circuit voltage is Norton current times Norton resistance. Now what's the slope of this line? What's the slope of this line here? Negative Rn. Okay? So we know that the slopes of these two lines have to be the same, and their y-intercepts have to be the same, which tells us what? Rn is equal to R Thevenin, so the resistances are the same. In is equal to what? V source or V Thevenin divided by Rn, which is equivalent to R Thevenin. Okay, so now we have two different circuits that are equivalent to all other linear circuits. Okay? Yes? How do I find the slope? So the slope of this expression is just the number that's multiplying the load current, right? So the load current is my x-axis here, and so the slope of it is just going to be the number that multiplies that x variable, which in this case is negative Rn. Clear? Cool. So let's do an example. I'm going to do it up there. One that we've seen a lot before. Turns out it's a very useful circuit. And you'll find if you continue studying circuits that pretty much every circuit you analyze can be boiled down to either a current divider or a voltage divider. So I've got this circuit. Some V source, resistance R1, resistance R2. What I want to do is find the Thevenin equivalent. We've already done this, right? Before. What is my V Thevenin? How do I calculate that? How do I calculate the V Thevenin for any circuit? It's the open circuit voltage across my two terminals, right? So I'm going to leave this as an open circuit. Now what's the voltage across this open circuit? It's a voltage divider, right? It's equal to the source voltage times R2 over R1 plus R2. Cool? Now there are two different things that we can do now. We can either calculate the short circuit current or the equivalent resistance. So let's do them both, just for practice. So now I take this, and I draw a short circuit current. Now where, I've got the plot handy right here, where on my curve is the short circuit current? Yeah. It's the x-axis. It's the x-intercept. This right here is the short circuit current because the voltage across the short circuit is 0, right? So when I short these two terminals together, the voltage across that is 0. Okay, so what's the short circuit current? For this circuit, It's just Vs, source voltage, divided by R1. Now what I can do is either say Req is equal to V Thevenin divided by the short circuit current, which ends up being R1, R2 over R1 plus R2. Or I can do the following. I can short my voltage source, and if there were current sources, I would open them. Right? I want to make this expression 0, so I can isolate this R. And then I find the equivalent resistance. So I can just look at it and say, what's the equivalent resistance across these two terminals when this is 0? And that, I can see from inspection, is R1 parallel R2. Okay, but now what I want to do is use this to my advantage. Okay? I want to use my Thevenin equivalent circuit that I've developed for this to solve the following problem. So I have my circuit. And I load it with some unknown resistance, or maybe it's just some resistance RL. Now what I can do is I can redraw this circuit. Everything that I already analyzed the Thevenin equivalent of, I'm going to put in a box and redraw it as what I had before. So I already calculated this, right? This is R1 in parallel with R2, and this voltage source is my previous voltage source times R2 over R1 plus R2. And here are my two terminals. I attach my resistance RL. Okay, do you guys see how these two are equivalent? Is that clear? I just took everything that was in the box, everything that I already analyzed, and turned it into the Thevenin equivalent circuit. So now what's the voltage across these two terminals? It's a voltage divider, another one, right? Now I have a voltage divider between the load resistance and my Thevenin equivalent resistance, okay? So it's RL over R1 parallel R2 plus RL times, I don't want to write the whole thing out, my Thevenin equivalent resistance. This is a very simple circuit, but it illustrates this concept. And now we have a lot of intuition for this, right? We have this final expression, yeah.
I still don't know, like, what are you putting in the box?
What am I putting in the box? I'm putting circuits in the box. All I'm putting is this voltage divider. That's what's in the box.
And then you use this, and then you take it, and then you do another, another VTH.
Yep, so the point I'm trying to make is that everything inside of this box doesn't matter. All that matters is my Thevenin equivalent. They're the same. But this way, it's much easier to analyze. So this is a very simple example, right? A voltage divider, is relatively simple to analyze, even when it's got a resistor attached to it. But you could imagine something pretty horrible in here. Power amplifier, something, your microcontroller, something like that. And we can simplify it to a voltage source and a resistance. So the point that I'm trying to make is, from a circuit's perspective, from the perspective of this load resistance, everything in the box is the same. Yeah?
R without the subscript there, that's RL, right?
Yeah, that's RL, sorry. Yep. R without the subscript. Now it has a subscript, thank you. Yep. That's just from the voltage divider. Okay? Cool. Now let's do a quick example. Another quick example. This one's slightly more complicated, and this one will involve dependent sources. And we'll see how those work in this context. So I'm going to draw a dependent source whose source voltage is A times some voltage V plus minus some voltage V minus. Okay? And I'll get to what those are in a second. I have a voltage V plus that I connect to ground. And I have a voltage V minus that I connect in the following way. I have some source voltage, V source, some resistance, and some resistance here. And then I'm going to treat this as my Thevenin equivalent. And I want to find the Thevenin equivalent circuit of everything to the left of my load. So here I have, let me just draw this as well, R1 and R2. Okay, so this is the circuit that I want to analyze. Specifically, I want to find how this circuit behaves depending on the load. Okay? It's clear? So how can I do this? So first I want to find V Thevenin, right? That's just the open circuit voltage. How can I find the open circuit voltage? Let's do it with nodal analysis. Okay? First off, how many nodes do I have in my circuit? Four nodes, right? I have a node here. I have a node here. I have a node over here. And I have my ground node, right? So remember again that there's an implicit connection between all four of these little three-line things, right? Everybody cool with that? Four nodes? So let's look at the currents into this node. I'm going to call this one just U for now. Okay, and I've already told you what ground is, so we can skip that step. I'm going to call this node U. And I'm going to draw currents out of node U. There are only two currents, right? Let's call this IU1 and IU2. So what's IU1? Very quickly. So some of the currents at node U are equal to IU1 plus IU2. Okay, everybody clear about that? Can everybody see this? It's kind of up against this wall over here. Can you guys see it over there? Cool. Now what's IU1? This is, of course, 0. What's IU1 equal to in my circuit? Yes. The answer is, it's whatever potentials at this node U, which I've already defined, right? It's V minus the source voltage, Vs, divided by R1. Is that clear to everybody? Right, so all that I've done is I've taken the voltage at V minus, subtracted by the voltage at this other node, which I know is just Vs, because that's what my voltage source enforces. So this voltage here is Vs at this node, relative to ground, of course. Right? So this is all relative to ground. So I take the voltage difference across this resistor, V minus, minus Vs and divide by the resistance, R1. Is that a little bit more clear? Yeah.
So the voltage at point U is V minus, right?
Yep.
But what is V minus? Why is it minus?
Why is it V minus?
Shouldn't it be higher and then go to lower point ground?
Not necessarily, right? I can pick whatever, it doesn't matter what the absolute value of this potential is. Whether it's higher or lower makes no difference, right? If it's a negative voltage, then it's a negative voltage. I just named it V minus, okay? Just the name that I called it. Okay? Now, what's the current IU2 in my circuit? What's that? So again, I'm going to define across my resistor a plus and a minus. What's the voltage at the positive terminal of my resistor? V minus. And what's the voltage at the negative terminal of my resistor? It's the dependent voltage source, right? It works just like a voltage source, but its voltage depends on other stuff going on in the circuit. Minus A times V plus minus V minus. And this all divided by R2. Is that clear to everybody? That's my node equation for U2, or for the node U. Everybody cool with this? So it turns out that if I look at this expression, I really only have one unknown in it. That's V minus. So let's just solve for V minus. This is equal to 0. And I can solve for V minus. I'm going to gather terms. I have V minus over R1 plus V minus, let's make them all consistent, V minus over R2. And what else do I know about this circuit? Do you guys remember what V plus is? V plus is just connected to ground. So this is 0. 0 plus A times V minus over R2. Okay, so I've just collected all the terms that have V minus in them, and I'm going to put the source voltage over on the right side. That's Vs over R1. Okay? All I did was massage that expression a little bit. Any questions so far? So I have V minus over R1, V minus over R2, plus A, my dependent voltage source doing work, Vs over R1. Okay, now I'm going to put these all together. V minus 1 over R1 plus 1 over R2 plus A over R2 is equal to Vs over R1. And I can just take this whole expression and put it on the other side, right? And solve for V minus. V minus is now equal to Vs over R1 times 1 over R1 plus 1 over R2 plus A over R2. Okay? Is that clear? So V minus is equal to Vs over 1 plus R1 over R2 plus A times R1 over R2. That's it. Am I done? Is this the open circuit voltage? What do I need to do to find the open circuit voltage now? If I told you what V minus was in this circuit, what would the open circuit voltage be? If I just say V minus is 1 volt. Yeah. Yes. The output voltage is A times V plus minus V minus. Okay, it's the difference in those two voltages. In this case, I have my expression for V minus. I've solved for it. So V open circuit is equal to negative A times this expression. Negative A V source over 1 plus R1 over R2 plus A R1 over R2. That's my open circuit voltage. I know it's pretty gnarly looking, but that's what it is. Everybody clear on this? Just nodal analysis, right? Just calculating the open circuit voltage. Yeah, you have a question?
How do you get from V minus to V open circuit?
How to get from V minus to V open circuit. So if you look at our circuit up here, the output voltage is directly connected, or sorry, that dependent voltage source is directly connected to the output, right? So the open circuit voltage will always be A times V plus minus V minus. So all that I had to do was go in and find what V minus was, okay? Because V plus is 0. Yes? Why is it a negative A? That's a good question. It's because of my dependent source, right? So a dependent source in this configuration performs an inversion. It inverts the voltage. Does that matter? I mean, it just means that my voltage is negative. Like, makes no difference to me. What is A? It's the scaling factor that I multiply the voltage difference between V plus and V minus. So that's a dependent source, right? I take an arbitrary number and I multiply it by a voltage or a current.
Actually, where is the V out?
Where is V out? It's labeled over there across RL. So that's the output voltage. Okay? Yeah.
What do you mean when it says it inverts the voltage? Like, why is it negative?
Right. So if I just directly connected the voltage source to V minus, the output voltage, and I had a ground at V plus, the output voltage would be negative A times V minus. Okay? A negative voltage is no different than a positive voltage, right? It's just opposite polarity.
Oh, is it negative A because we defined it the other way around?
Yeah, we define it as that dependent source is taking the difference between these two voltages. In this case, it takes the difference, 0 minus whatever voltage is at V minus, and it multiplies it by A. You guys seem a little nervous about a negative voltage. Why is that? Is there any reason in particular? Negative voltages seem weird. If you take a multimeter and you measure the voltage across a battery, like this, let's say, I'm going to draw it really small over here. I've got my battery, and I take my voltmeter, and I plug it in like this. Let's say it's a 1.8 volt battery, for example. I take my positive, my red wire, and I hook it up to here. I take my minus wire, I hook it up to here. I'm going to measure 1.8 volts, right? Now what happens if I flip the two terminals? I put my minus terminal here and my plus terminal here. What am I going to measure? Negative 1.8 volts, right? Nothing scary about negative voltage. I just flip my reference, okay? Cool? Now for this same circuit, discounting RL, right? RL is my load resistance. What is my Thevenin equivalent resistance? This is a little bit tricky. But I don't have to do any analysis to find it. What's the equivalent resistance? Yeah?
Just drop Vs from the expression.
You just drop, so that would give me the output voltage. So what I want to do is, when I calculate the output resistance, let's do it. for practice. When I calculate the output resistance, what I want to do is short out all the sources, independent sources in my circuit. Independent, very important. And calculate the equivalent resistance. Right, so previously I had something that looked like this. A V plus minus V minus. Here's my V minus. Here's my V plus. I take this, and I want to find the equivalent resistance between these two terminals. Okay? Vs, R1, and R2. So what's my procedure? First, I zero out all my independent sources, right? This turns into a short circuit, right? Short circuit. So now what's V minus? 0. There's no more currents in my circuit. There's no more voltages in my circuit. V minus is 0. Which means what about my voltage source here? This also becomes 0, right? This is gone. Which means that I can redraw it as my output terminal with a short circuit directly to ground. What's the resistance of that? 0? Yes, 0. Zero. No output resistance. No Thevenin equivalent resistance. That's pretty cool, right? So what I did was, I took that voltage source, which maybe had some resistance attached to it, I attached it to my circuit, and now my equivalent circuit no longer has a Thevenin resistance. Pretty cool, right? So we'll learn a lot more about that circuit, that particular circuit element, specifically that dependent voltage source, in about 1 week, maybe a little bit less. It's a very, very helpful circuit. Okay, everyone clear on this? Yeah?
Does this mean that voltage current graph is a constant line straight across?
Yeah, what does our voltage current graph look like? Let's draw it out. Here's the current I load. Here's the voltage. I know that my voltage open circuit is that expression. It's actually negative, so let's draw it down there. It's negative A times that expression, right? And because the resistance is 0, it looks like this, where this is the Thevenin voltage, VTH.
So no matter what you do with the voltage, you always get the same current.
Other way. Exactly the opposite of what you said. So he said, no matter what you do with the voltage, you get the same current. It is, in fact, the inverse of that statement. Whatever you do with the current, whatever current I load this circuit with, I get the same voltage. It acts like a voltage source. Okay? That clear to everybody? No output resistance. Yeah, you have a question?
Why did you short circuit the voltage source when you did short circuit? Because I thought when you're doing the Thevenin equivalent stuff, when you do the open circuit and short circuit, you have to do it at the output area.
Yeah, so what I did instead of finding the short circuit current is I directly computed the Thevenin equivalent resistance. Okay? So if in general you want to calculate the equivalent resistance, so the general procedure goes something like this. And it all comes down to that expression that we derived from superposition, right? If I've got some box of circuits, and I want to find, draw it like this, the equivalent resistance, or the Thevenin resistance, what I need to do is, first, zero all independent sources. So any voltage source becomes a short circuit. Any current source becomes an open circuit. And then either I can just see it from inspection, which hopefully is the case, but if it's not, what I can do here is do it just like an ohm meter would. I attach a voltage, V test. I measure how much current that voltage source needs to provide. And I say, here's my second step, either inspection or attach this voltage source V test and measure I test. The equivalent resistance will then be V test divided by I test. And that again is the slope of my IV characteristic line. Yeah?
So if you can't figure out the equivalent resistance by inspection, then you have to do it like empirically?
Yeah, so empirically, yes. So if this were a circuit in the lab, I would take an ohm meter. Somehow I would short out all my voltage sources, open all my current sources, independent ones only. Dependent ones I have to leave, okay? And then I would take my ohm meter, which is actually a voltage source that measures its own current, okay?
So like, if we got like a problem where we wouldn't be able to like empirically determine V test or I test, that means we have to be able to figure out by inspection what the equivalent resistance is?
Not necessarily by inspection. You can always do this second step. I just recommend that you look at, oftentimes you can see this quite easily. Like in this example, we can see it pretty much immediately that it's just a direct short circuit to ground, which means its resistance is 0. Okay? Yeah.
Wait, isn't resistance like a feature like that's related to the like a material that's made of resistance? How could resistance be?
Yeah, that's a great question. So the question was, isn't resistance something that's associated with a material? It's like a resistivity times the length of the material divided by the cross-sectional area. So the answer is yes, definitely. But we also, what we've done is we've abstracted beyond that point, right? What we do, so fundamentally, when we draw a circuit on the board, it's an abstraction, right? It's our model for something that's happening in real life. Now, on top of that, we've added a further layer of abstraction, which is we've taken that result and turned it into an equivalent Thevenin model, okay? So its resistance, that resistance is not real, right? It has nothing, well, it has stuff to do with what's happening in the physical world, but it's basically our way of interpreting resistance, okay? Does that answer your question somewhat? It's a very good question because fundamentally we're talking about like multiple layers of abstraction on top of each other, right? This Thevenin resistance, this being a short circuit, is not real. That's not real life. But it is for the sake of our analysis. It works. Okay? Yeah?
Why can't we zero all the independent sources? Like what was the...
Yeah, so let me write out that expression again. I'll do it over here. Why do we zero out all of the independent sources? So let's take an example with 2 sources. Or actually, let's just do 1. So this is our example, right? We've seen this circuit a whole bunch of times already. And I want to eventually be able to attach this load current IL, but I'm not going to worry about that for now, right? Because all I want to do is find the equivalent circuit here. So I know that V out V out is equal to, it's Vs, so my source voltage divided by times R2 over R1 plus R2, not divided by, multiplied by, excuse me, which is some alpha times Vs, right? And that's assuming that there's no current source loading the circuit. So now I'm going to add that in. And what that's going to do is V out now becomes, I'm going to attach to this expression some current IL multiplied by some mysterious resistance R Thevenin. So if I want to isolate R Thevenin, that's something that I want to solve for, I have to get rid of any dependence that the output voltage has on independent source voltages and independent source currents. Yeah.
Why is it that when you add the current source, you subtract it from that side?
Yeah, so if we look at superposition, and let's say that this is a real-life current source, so my circuit actually looks like this. By superposition, if I look at this circuit, short out this voltage source, there's going to be some voltage at the output, dependent on the current, and also multiplied by some resistance, right? That makes the units work out. Okay? So I can actually go in and solve for it, or I can get it from finding the equivalent resistance there. They're all the same. Does that sort of clear things up a little bit? So it all comes down to superposition. So for a general circuit that has a whole bunch of voltage sources and a whole bunch of current sources, by superposition, I can say that this voltage at the output is equal to a sum of alphas times voltage sources. So I think I used n m plus a sum n of some response to current sources, right? That's open circuit. Now I add this load current, and I subtract I load times my Thevenin resistance. Okay, does that clear things up a little bit? All comes down to superposition. Yeah? What do you have to do if you have dependent sources? That's a good question. So dependent sources they mess things up a little bit. The answer is that you cannot do superposition with dependent sources. The fundamental reason behind that is, if you remember the sort of AX equals B representation of our system of equations, the dependent sources are actually part of that matrix A, rather than part of the vector B. So independent sources are in B, so I can just have B equal some sum of B's and freely invert the matrix and have the result be the sum of those inversions. But I cannot make fundamentally changes to A. That changes my network. I'm no longer solving the same circuit. Yeah?
I'm still kind of confused of the previous example. Just to find R Thevenin, you have to apply a v-test, right? Let's assume we apply v-test on that graph.
Yeah.
It's still 0.
So let's do it, just for practice. It's a good practice problem for the last 10 minutes in the class. So we'll go back to this. We call it an inverting amplifier. I've got my V minus, my V plus, and I'm going to go ahead and short this voltage source, right? Because that's what I have to do to find the equivalent resistance. R1, R2, here's my A times V plus minus V minus. And here I have my voltage source V test. Okay? So we've got a problem here, don't we? What's the problem? I have two voltage sources in parallel, right? That's not good. So what's the voltage at this node? Which one wins? AV plus minus V minus or VT? There's no way to tell, right? The only way that this circuit is valid, that it has a solution, just like very abstractly, is if this is a short circuit and then the current is infinite, right? This current is either 0 or infinite. Okay? It's 0 if A times V plus minus V minus is exactly equal to VT, and it's infinite in all other cases. All right? So now I've got this I test is huge. So I have R Thevenin is V test over I test, which is the limit as I test approaches infinity of V test over I test, which is 0. Okay? The reason I didn't want to do it this way is because it's not intuitive, right? Putting two voltage sources in parallel is very bad juju. Don't do that. Okay? Does that answer your question? So that we've explicitly calculated, to the best of our ability, the output resistance of this circuit. More fundamentally, though, you can think about it this way. If instead of a voltage, I'm going to do it over there. So I'm not even going to draw the rest of the circuit. I'm just going to have A V plus minus V minus. Here's my port, my terminal. If instead of supplying a current, I load it, or excuse me, instead of supplying a voltage and testing how much current that has to supply, instead I draw a current out of it, and I measure what the voltage is then. If I draw a current out, no matter what that current is the voltage going to change? No, it's attached to a voltage source. So that's another interpretation that this has 0 output resistance. The Thevenin resistance is 0. Okay? So everything is meshing now. It's good. This is a more appropriate way to analyze the circuit. Yeah? Sure. So we have, if I take a battery, a perfect battery, a voltage source with 1 volt of voltage, and I attach this to, in parallel, another voltage source, 2 volts. Which way is current going to go? From 2 volts to 1 volt, like this. So I have a voltage difference between these two, and what's the resistance across here? 0. So what's this current going to be? Infinite, right? In my abstraction, this voltage is infinite. If you do this in real life, your wire will have some finite resistance, okay? And either, if your voltage supply doesn't have a current limit, then it will probably light this on fire. If it does have a current limit, it'll hit the current limit. Okay? And that's exactly why in the labs you set current limits to 100 milliamps. I think it is 100 milliamps. Okay? Because if you accidentally make a circuit like this, it could cause damage. It could damage this voltage source, it could damage the wire, it could damage the lab or you. Generally is bad. Electricity can be dangerous. Okay. So let's summarize the lecture today a little bit. Talk about what exactly we talked about. Fundamentally, we did a couple of examples, first of all. And we combined this concept of superposition, linearity, equivalence, all that into basically saying, and I'm going to draw this box again. I've got some voltage that I measure across here, V, that's dependent on 2 things. voltage is dependent on whatever is going on inside of this circuit plus this load current. And because of superposition, I can look at those two things completely independently, right? If this is linear circuits, that voltage is a function of all the supplies in here plus my load, right? Is that clear to everybody from superposition? So what I can do is redraw that box as an equivalent voltage and equivalent resistance, where the voltage, again, is purely determined by the circuits here, that Thevenin voltage, and the current, or excuse me, the resistance, is the slope of the line as I vary this load current. Okay? I can also draw it, so this we call Thevenin. I can also draw it as a current source with a parallel resistor. So this is I Norton, and this resistance, you remember we derived it, is actually equal to R Thevenin. And just really quickly, does this make sense intuitively? Let's say I take my ohm meter, I turn off all the sources in my circuit, and I measure across these two terminals. In this case, turn off all my voltage sources, it's a short circuit, right? And I measure R Thevenin. In this case, what do I do with my current source? I leave it open circuited, so this is gone. And what's my equivalent resistance? Again, R Thevenin. So these two have the same resistance. Norton. Okay? Everybody cool with these fundamentals? Any questions? Yeah.
In this example here, R Thevenin ended up being 0, so how does that define your I?
I Norton? Yeah, so the question is, in the previous example that I did, the one with the so-called inverting amplifier, my output resistance ended up being 0, right? What does that mean about my Norton current? What is it? Just strictly by the definition of the Norton current, right? It's a V Thevenin divided by R Thevenin, right? R Thevenin is 0, so the current is theoretically infinite. So it's not really an appropriate expression to use. So we can't necessarily always do this, so if I have a perfect voltage source like I did previously, this doesn't quite work, okay? Because if I have an infinite current and I attach it to a finite resistance, what is that? I don't necessarily know, right? I don't know the answer to that question. Yeah.
Yesterday, I just want to know the difference between today's and yesterday. Yesterday, the way we did was to measure the I out.
Mm-hmm.
So, and we didn't short the voltage source though, like in original.
Good question. Okay, so what we did in the other case was we calculated, so yesterday we talked about basically 3 different ways of calculating equivalence. One is open circuit voltage, one is equivalent resistance, which we talked about here, and the third is short circuit current, right? So with short circuit current, what we do here is we say, okay, I don't know what the current at the output is, but I'm going to draw a short across here. And what that basically means is I want to find what the current is when the voltage across these terminals is 0. So if we look at, we know that our curve looks something like this. Here's my I load, here's my voltage. I know it has this shape. And so what I'm doing here is I'm finding this point. So rather than calculating this point and the slope, so this point is V Thevenin, this point, it turns out, is I Norton, right? And this slope is minus R Thevenin. So we're basically explicitly calculating I Norton, right? That's all. That's the only difference. Really, there's no difference. They're all the same. Like, what's stopping me from finding some point here? In principle, nothing. It's just these are the easy ones, right? Make sense? Everybody cool on Thevenin and Norton? You'll get a bunch more examples and discussion. That's all I got for you today. Next week, we start on capacitors. That's going to be fun.